Hey everybody, welcome to your second part, as promised, of Oceanography Final Exam Review. So we're going to be going over the study guide, and hopefully we'll get through this in less than an hour, I hope. Fingers crossed. But I don't want to bore you with any more introductions, so better get right on to the subject matter at hand. Got your final exam study guide, which I hopefully handed out in class to you. And you have a hot little copy in your hand. And let's go through this. So we're on physical properties of water. And we're starting off. I did explain this in class, but that's okay. We'll go over it one more time. What is the chemical formula of water? Please draw out the molecular structure. Include the angle between the hydrogen atoms. Of course, I hope you know by now that H2O is the formula of water. Do hope you know that. And of course, you should know that angle, that magic angle between the water molecules. Here's the oxygen. I'm sorry, not between the water molecules, between the hydrogens is 104 degrees. Okay, so that's that magic angle. And you might ask, why does it have that angle? Well, remember that oxygen. Okay, that's my oxygen nucleus. And remember that it has its element number 8. So that means it has 2 electrons in the first shell, and it has 6 in the subsequent shell. And the way that electrons like to gather together is they like to be in pairs often. So you'll have 2 pairs, which are non-bonding pairs because they are, I don't want to go too in depth into how electrons bond and everything, but you'll have pairs that are not going to be involved in bonding. And then you'll have 2 electrons here that are by themselves. They're lone. They're by themselves. And they like to bond. So they'll get with the hydrogens, okay? So those will bond with the hydrogens. And the way it works is that you got to remember that electrons, of course, are negatively charged, and they all repel each other, right? So you can imagine that these pairs of electrons want to be as far away from each other and as far away from the hydrogens as humanly possible. Well, the fact of the matter is, if you have a central oxygen atom, you're going to have one of the hydrogens here, and everything's going to kind of arrange itself in this sort of tetrahedral structure. It looks a little bit like a pyramid, but it's not really a pyramid. So you have a hydrogen there, you have a hydrogen here, you have one of the non-bond pairs of electrons there, and you have another set of the non-bond electrons there, okay? So you'll notice that this angle right here between the 2 hydrogens is not 90 degrees. I'm sorry if it looks 90 degrees. It's not supposed to be 90 degrees, but it is 104 degrees. We're pretty close to 90 degrees, but it's actually 104 degrees. So if I were to show you this, let me just type in really quick here. Let's see. I want to look up tetrahedral structure. You'll see how this is kind of oriented. Here we go, like this. Let me just kind of show you a tetrahedral structure so you have an idea about what this would look like, okay? But you could imagine like one of the hydrogens being right here, one of the hydrogens being right here. This is one of the pairs of lone pairs of non-bond electrons and another pair of non-bonding electrons here. And you would notice that there would be a, right here, an 104 degree angle between the hydrogens, okay? So that's why water has the unique structure that it does, and that's why it has that non-90 degree angle right there. And that's also why it's not in a straight line, too. And actually, if we did this whole exercise for like carbon dioxide, you would see why it is in a straight line, but water is not, okay? So anyway, is water a polar or non-polar molecule? That's the next question here. Oh, by the way, one last thing before I move on away from 79. Just make sure that you know that, this is going to be a short answer question. I can't guarantee it's going to be one that is on your test because, of course, it draws from a question bank. But it's on that question bank, so make sure that you can answer number 79, just like I repeated for you here. Just make sure that you mention something about non-bonding electrons and how they repel each other, and everything kind of gets pushed as far away from each other as humanly possible with the hydrogens and the 2 sets of non-bond pairs. Okay. All right. So next is number 80. Is water a polar, non-polar molecule? Gosh, I hope you know that by now. It is, of course, a polar molecule. That creates a lot of its funky characteristics, right? Like its high heat capacity and its surface tension and things like that. So it's because it's a polar molecule, okay? Now please label each of the arrows, two names of two processes that correspond to the phase change indicated. So a lot of these things, this is going to phase changes of H2O. A lot of these processes you probably know just from everyday life. Some of them are a little bit weird. So water goes to ice. I'm sure you know that water going to ice is just freezing. You know, back from going ice to water is melting, all right, you know that, that's obvious. Water going to water vapor is, of course, evaporation, but water vapor going to water, some people don't know that one, that's condensation, okay? Now, a lot of people don't know these processes down here that skip the liquid phase and go directly from a solid to a gas or a gas to a solid. That's called sublimation when you go from a solid to a gas, and then it's called deposition when you go from the gas to the solid phase. Okay. Now, one thing is that latent heat gets into the mix here. Latent heat's really important to understand. It comes up a lot in this class. So latent heat, of course, is the energy that is stored in the bonds between the H2O molecules. Okay, so when they change phase, they go from whatever, from a solid to a liquid or a liquid to a gas, etc., they're going to either release or absorb that latent heat from the environment. Okay, so it's going to actually change the temperature of the environment as water molecules change state. Okay, and it's either going to make it cooler or it's going to make it hotter. All right, so now basically the way that you should remember this is if you're moving from the left to the right and you're going from a solid phase to a more gaseous or liquid phase, going towards the gas phase, then you're going to be subtracting energy from, you're breaking bonds, and that takes energy. So it's actually subtracting energy away from the environment. So this is always going to make things cooler as you go from a solid phase towards a gas phase or a liquid phase. Vice versa, if you go the other direction, you go from water vapor from a less condensed to a more condensed solid phase, then you're going to be heating things up because you're going to be forming the bonds, okay? So this is going to be heating, all right? And and I think a way that I remember it that's kind of easier for me is that it always, whether it's heating or cooling, it always contradicts or goes against kind of what would normally be happening to move from a solid to a gas or a gas to a solid, right? So, you know that like to go from ice to a gas, you need to heat things up, but it's always going to the latent heat release is always going to counteract that. So it's going to keep things cooler. So it's going to tend to counteract the force that's moving it to either the solid or the gas phase or whatever it is. Okay, so anyway, enough said about that. You do need to know how that latent heat is transferred as H2O changes phase. Okay, so we've covered 82 there. 83, where in the ocean in terms of latitude does evaporation outpace precipitation? Remember that this is in the tropics, okay? So tropics is big time. We're getting a lot of evaporation. That goes back to atmospheric circulation patterns that we talked about in the location of the STH in the subtropical high. We talk about that later in the atmospheric lectures, okay? So atmospheric circulation lectures. Vice versa, where's the ocean actually having more precipitation than evaporation? So that's going on at higher latitudes, maybe like 45 degrees and above, maybe 45 to 66 degrees. That's where you're getting more precipitation outpacing the evaporation. So that's important because basically what you're doing with that is you're moving heat in the form of latent heat from the tropics where it's hot to these higher latitudes where it's cold. So it actually works to keep the temperature of the Earth and the climate of the Earth more equilibrated. Okay, so that's why H2O is so important for our planet. Otherwise you'd have these crazy extremes, the tropics being unbearably hot, and the higher latitudes, 45 degrees, 66 degrees, just being unbearably cold. Okay, so it makes the planet basically much more habitable. Now, 85, at what latitude is the ocean releasing heat? At what latitude is it being released? So I just covered that right up above. I just explained that. So moving on to 86, why does the land heat up more rapidly than the ocean? I actually showed this slide like 4 times in this class, so it's important, right? So you got to know this stuff. Why does the land heat up more quickly than ocean water does typically? So there are a few reasons to this. For one thing, that oceans are transparent, or not, I shouldn't say transparent, maybe translucent is a better word for it, but the solar energy penetrates, suffice to say, penetrates into the ocean. So because it penetrates into the ocean, that heat from the sun, from the solar radiation, is spread over a very thick column of ocean water. Whereas on the land, you don't have that situation. The solar radiation is just heating up maybe the top, inch of the ground, okay? Because that solar light can't penetrate down into the deeper levels of the land. So the oceans are transparent or translucent. That's one reason. Oceans mix, right? So hotter and colder layers can mix, right, to heat and spread that heat around more efficiently. So it takes more time to heat up the oceans, therefore. Whereas that doesn't happen with the land, right? You don't have the dirt mixing with layers of dirt above it, okay? So there's no mixing. Another reason is that you have latent heat, right? So latent heat is, of course, going to be, I should actually be more specific and say evaporation, okay? Over the oceans, you have evaporation. Like I said, remember, it's always the release or absorption of latent heat is always counteracting the whatever force is moving it from one face to the other. So when you have the sun heating up the ocean, that latent heat of evaporation is going to tend to suck out that energy. So remember, evaporation cools everything down. That's why you sweat, right? So the evaporation cools your body down when you sweat. Same way, the ocean, when it evaporates its water off, it cools down the ocean, okay? So there's that latent heat. There's also the you noticed that I talked quite a bit about high heat capacities of water. So that's another place where it comes up. Remember, heat capacity is how much energy it takes to change the temperature of a substance. Now, for water, it has a freakishly high heat capacity, very, very high compared to most materials of Earth. And that has to do with the fact that it's a polar molecule. Remember, that keeps coming up. It's a polar molecule. It's a polar molecule. So that high heat capacity really takes a lot of the energy from the sun, and it sucks it up. It stores it. It's high, heat capacity, right? So it's the capacity to store heat, and it makes it a lot harder to warm up the oceans, okay, or cool down the oceans, vice versa. All right. So moving on. What's the density of the water? You should know that it's 1 gram per cubic centimeter, 1 gram per cc. What are some factors that affect density of water? It's the salinity, and it is also the temperature. The temperature is the more important one, okay? So make sure that you know not only which are, the two factors, but that temperature has the bigger effect, okay? Salinity just kind of tweaks it a little bit, but temperature has the biggest effect. Okay, what are some things that affect ocean salinity now? So now we're going to zoom in on salinity, say what are some things that can affect it? Well, there's at the high latitudes, there's ice formation, right? This is like sea ice formation. Think of like the Arctic or Antarctic circles, okay? So ice formation and ice melting. So ice formation, remember that when ice forms, it basically forms that ice out of pure water. It doesn't take the salt into its ice structure. So it leaves the salt behind. And that means it's going to make, as the ice forms, it's going to make the residual water saltier. Vice versa, ice melting is going to do the opposite effect. It's going to make the water less saline. It's going to make it more, I don't know what you want to say, fresh when it melts, okay? So another process or pair of processes that occurs, also evaporation / precipitation. So evaporation, of course, tends to make the ocean saltier. Remember, when you evaporate the water, it doesn't take the salt with it. It leaves the salt behind. So the residual water gets saltier. Precipitation, on the other hand, dilutes the surface water, right? So when precipitation, rain falls, of course, that salt water doesn't fall from the sky. That would be horrible. It's fresh water, so it dilutes the saltiness of the upper ocean. The last thing that you want to put here is runoff. So you have these kind of two pairs of processes that go with each other, and then you have runoff. Runoff only makes the ocean less salty. Okay, so where you have streams coming into the ocean locally, it makes it less salty. because you just have this big influx of fresh water, or relatively fresh water. Depends which river you're talking about, but for the most part, it's fresh water. All right, now what happens to salinity with depth at high latitudes, and why does that happen? So salinity in most parts of the ocean actually starts off high, and then it decreases with depth. And that's because there's a lot of evaporation at the surface, and that high salinity water is being buoyed up by the thermocline. But that doesn't happen at high latitudes. Okay, at high latitudes, you have the opposite trend. You have salinity increasing as you go deeper and deeper and deeper into the water. And that's because, as I've often said, there is no thermocline, right? There's no thermocline at that high latitude, okay? So without a thermocline, there's nothing to support the salty water. So salty water just immediately goes down to the bottom and sinks, all right? Now, what do you call that dramatic change in salinity with depth in near surface waters? Just like the thermocline for temperature, we have the halocline for salinity, okay? So usually you have this really dramatic change in salinity as you go down, but it kind of depends where you are on Earth. But usually you have a very dramatic change in the salinity as you go down to the depths, okay? Now, what do you call the dramatic change in temperature? Like I said, that is called the thermocline. I wrote it up here. That's the fact that arises from the fact that the sun is heating up the ocean from above, and so that hot water, relatively hot water, tends to float, right? It's less dense, it's more buoyant, so it tends to stay on top. All right, now, how does temperature change with depth at the equator and the tropics, and why does that change occur? Just like I was just explaining, at the equator and tropics, where you have a lot of solar radiation, a lot of sunlight, you get a lot of high temperature hot water sitting on top, and as you go down, the temperature just plummets really quickly. Okay, so by the time you get down to like 1,000 meters, basically you're almost at like ice cold waters, right? And that trend occurs because, right, the sun is heating things up from on top, and that's what ends up happening is the hot water is not going to sink because the hot water is less dense, it's more buoyant, it stays up on top, and the cold water stays down there, okay, because it's more dense. All right, now 94. How does temperature change with depth at the poles, and why is that change occur? Now, of course, at the poles, everything's different because at the poles it's cold. It stays cold as you go from the surface all the way down to the bottom. It's basically the same temperature. So, like I said, there's no thermocline here, no thermocline. It's cold on top, it's cold at the bottom, and because of that, if there's any salt water that gets generated, it immediately just sinks. And that's why you get more at the poles, you get a increase in salinity with depth instead of the normal decrease that you get in other parts of the world. Now, 95, how's that trend of density, how's that density change, getting myself all tongue-tied. How does density change with depth at the poles versus low latitude waters? Okay, so why do we see that trend? So at the poles, there's actually no pycnocline. Okay, so pycnocline is the change in density with the change in depth. Just like there's no thermocline, there's no pycnocline either. So and it's because you don't have the thermocline, so you don't have the sun heating things up from on top. So in the tropics and in the equatorial waters, you have really hot water sitting on top, and it's gravitationally stable because it's, again, I've said this a million times now, it's less dense, it's more buoyant, so it stays up there on top. So that's less dense water. As you go down, it gets progressively denser. You don't have that effect in the poles because at the poles, it's cold on top, it's cold at the bottom. There's no temperature difference. There's really not much of a density difference either. There is a salinity difference, but like I said, salinity doesn't actually play a huge role in density. It just kind of tweaks the density a little bit, whereas temperature has a much higher effect. All right. Moving on to ocean water chemistry. It says, what's the percentage of salt on average in the ocean? Boy, make sure you know this, not only in terms of percent, but also in a few different ways. We'll go over all of them. Make sure you know it's 3.5%, 35 grams per per kg of water slash aka per liter of water. Kg of water is a liter of water, okay? Another way of expressing this is 35 per mil, okay? So those are all different ways that you should know how to express this. 7 common ions in seawater. Make sure you know all of these. Of course, the big ones are sodium, chloride, magnesium, and sulfate, right? Those are the big 4. Make sure you know those. But there's also carbonic acid, and there's also boric acid. There's also strontium. There's also fluorine. Did I get all? Let's see, that's 4. Oh yeah, I got more than enough now. So, and there's also, oh, I'm sorry, getting kind of weird stuff. Before I even mentioned those, there's also calcium and there's also potassium. So I'm sorry, you should really know sodium, chlorine, magnesium sulfate, calcium, potassium, and then carbonic acid, boric acid, strontium, fluoride. That's a lot more than what you even need. So anyway, but I put them in order for you. So then next one, it says, where does salt in seawater come from? The 2 sources. So the salt comes from either runoff, right? Runoff from rivers, and the other source is volcanic outgassing. And you know that there's a lot of volcanic outgassing going on at the mid-ocean ridges. So I'm going to just put here mid-ocean ridges. Whoops. I'm going to change my pen color because I notice this black pen is very, it's a lot of like very buggy, has like causes kind of glitches and bugs in the system. Okay, anyway, what ion is more concentrated in stream water than ocean water? Why is that? That component that we studied is SiO4 or silica, okay? So that's it. All right, moving on to atmospheric circulation. So what are 3 abundant non-variable gases in our atmosphere? Also know a little bit about their relative abundances. So that, of course, is oxygen at 21%. And nitrogen is the most abundant. Don't forget that. That's 78%. And then you have argon at a mere 1%. Okay. Now, how does the density of the atmosphere vary with elevation? So density goes down with so it's an inverse relationship. Density goes down with an increase in elevation. Now, why are temperatures normally lower at high latitudes? Okay, I don't know why this is right here. This is not the right place for that ecliptic plane question. Sorry, it's just kind of tag along there. But why are temperatures lower at higher latitudes? This is an important question. So a lot of people, I don't know why they think that somehow this has to do with being maybe further away or closer to the sun. Has nothing to do with that. The reason is that at higher latitudes, sunlight is coming in at progressively higher angles. Okay, so you can imagine that when you're at the poles, sunlight coming from the left in my diagram is hitting you basically at almost not a 90-degree angle, but almost like a 0-degree angle. So it's coming in at a very low angle. So that sunlight ends up getting spread over a larger area. So maybe another way that I could show this, I think this is actually a pretty good way of depicting this. Boom. Okay, let me draw my circle again, like a semicircle like this. Okay, there's my semicircle, okay? And then what I'm going to do is I'm going to get the highlighter, okay? So this is going to be my ray of sunlight. So here's a ray of sunlight coming, okay? And then it's hitting about the equator, all right? And then let's do another ray of sunlight, same thickness, and it's coming in near the poles, okay? So I want you to notice something here. Notice how that same ray of sunlight, same thickness, is being spread. Whoops. This thing gets all buggy. It's being spread over this much area, and over here that same ray, same thickness of sunlight is being spread over that much area. So do you see how up here at the high latitudes, how that solar radiation is getting spread over a larger area. So it's the same amount of solar radiation, but it's spread out. So that's why it's actually colder at higher latitudes. It has nothing to do with being further, closer to the sun. I don't care what Miss Frizzle says. It has nothing to do with that. Anyway, moving on. How does density of the atmosphere vary with elevation? So just like, oh wait, we already did that. Density of the atmosphere with elevation. So I'm sorry, that's a repeat. How does air pressure vary with elevation? Same as density, it goes down. So air pressure goes down, elevation goes up. Density goes down, elevation goes up. Okay. Now, how does temperature vary with elevation? Same thing. It goes down as elevation goes up. Now, that trend actually reverses once you leave the troposphere and go into the stratosphere, but you don't have to worry about that. But for the troposphere, that's why I put here specifically the troposphere, because it's not a simple relationship. But for all intents and purposes in this class, temperature goes down as you go up in elevation. What's that rate of temperature change called? It's called a lapse rate. Why does it get colder as you go up into the troposphere? Well, for the same reason, if you have see, I have this sitting here at my desk because I clean my stuff a lot. For the same reason that if you ever use one of these compressed air cans, to clean up your desk, to clean up your keyboard, you'll notice that actually, hey, I can actually do this for you because I have the thermometer too. Oh, sorry. But anyway, you'll notice that this is a digital thermometer. It'll read the temperature. And if I read it, you'll notice that's, 78 degrees, okay? So then I'm going to spray it. And I'll take the temperature again. And now you notice it's 57, 58 degrees, okay? So it got colder, right? And it got colder because it decompressed, okay? So when you decompress a gas, it gets colder. That's called adiabatic cooling. And that's what happens to air as air rises through the atmosphere. As air rises through the atmosphere, pressure goes down, so it decompresses, and it cools. It cools adiabatically. It's called adiabatic cooling. So anyway, it cools, it'll hit the dew point, and then you can get precipitation forming. Okay, moving along, what is the ITCZ? So the Intertropical Convergence Zone, or ITCZ, is a belt of high humidity and high precipitation that occurs roughly around the equator, although it shifts seasonally. But anyway, this is a place of very high heat, receives a lot of solar radiation. It's near the equator, and air is constantly rising there. So it's rising, and as it rises, the air also has a lot of humidity. It's hot at the equator, right? So you might remember that hot air can hold more water. So that hot, humid air rises, it cools adiabatically, and then it hits the dew point and you get precipitation, rainfall. So whenever you see the picture of the Earth from like a satellite or space view, you'll notice that there's like always a belt of clouds that goes around the equator. That's literally, you're looking at the ITCZ, okay? So that's why there's a lot of precipitation there. I just explained that. All right, what's the name of that global wind cell in which air rises at the ITCZ, it descends at the tropics? That's called the Hadley cell. Okay, I don't like this big, thick pen. Let me get a boop, draw. There we go. All right. Now, what's the subtropical high? So you know that whatever goes up must come down. So air rises at the ITCZ, right? So there's the air rising at the ITCZ. Okay. But then it's going to go either to the north or to the south or vice versa. And it's going to come down again at the horse latitudes, about 30 degrees north and 30 degrees south. And it's going to return again. So where it comes down, remember, descending air creates a high pressure system. So that comes down at the STH, the subtropical high. Okay, 30 degrees is about subtropical. 30 degrees north, south, that's a latitude. It's about subtropical, so we call that subtropical high, STH. Okay, so when that air returns down, instead of adiabatically cooling, it'll do the opposite. It will adiabatically heat up as it descends. So, and as it descends, remember that because it precipitated all its moisture out and condensed out all its moisture here at the ITCZ, so I'll draw a little happy little rain cloud up here, raining. Lots of condensation, that added latent heat to the air. So it comes down at the STH a lot hotter than how it began, and with a lot more energy. So that creates high temperature, dry air coming down at the STH, and that's what causes all the evaporation to make the ocean saltier at the tropics. Okay, so if you ever wondered why the ocean is saltier at the tropics, that's why. Okay, it has to do with these global air cycles. All right, what are the trade winds? What causes them? So as that air returns to the STH, it goes, once it comes down at the STH, it returns back to the equator, and that's what forms the trade wind. So it travels over the surface of the Earth, and it's traveling over its surface and creating those trade winds. Okay. All right, what's the Coriolis force? So you know that air, whenever it tries, or any fluid, air or water, tries to go in a straight line on the globe, it always gets deflected to the right in the northern hemisphere, to the left in the southern hemisphere. So that's the Coriolis force. That fictive force, or it's not in a way a real force, but it just arises. I don't want to say it's an illusion, but it arises from the rotation of the Earth. In fact, the Earth is rotating beneath these fluid movements. But anyway, that's what the Coriolis force is. It's always going to deflect fluid movements, whether it's a water current or an air current, from a straight line motion going to the right in the northern hemisphere, to the left in the southern hemisphere. So we already answered that one. We already answered trade winds. Westerlies are the winds that, so if we go back to this diagram, or I can just draw it again, okay. We have at the equator, we have the ITCZ, air is rising. It moves either to the north or to the south, and then it comes down at the about 30 degrees north or south. Okay, and then half of that air goes this direction to form the trade winds. Half of it goes this direction to form the westerlies. Okay, so the westerlies are high latitude wind patterns. They're predominating at maybe 45 degrees north and south, maybe all the way up to 60 degrees north and south, and they are coming out of the west, blowing towards the east. Okay, opposite of the trade winds, which blow from the east towards the west. All right, going on to ocean circulation. What is a gyre? A gyre is one of the 6 large ocean patterns, right? Ocean circulation patterns that we have. So they go like this, right? They go, boom, in the northern hemisphere. Here's the equator. And of course, you can predict that they're going to be going clockwise here in the north. They're going to be going counterclockwise in the southern hemisphere. Okay, so there are these large-scale circulation patterns in the ocean. We have 6 of them. You should know those 6. So there are there is the North and South Pacific Gyre. There's the North and South Atlantic Gyre. There's the Indian Ocean Gyre. Of course, we don't have a North Indian Ocean, right? The Indian Ocean is completely in the southern hemisphere, just about completely in the southern hemisphere. And then we have in the Southern Ocean, we have what's called the windward drift, and that, aka the Antarctic circumpolar current. So that's the 6 gyres. Okay, moving on here. So why do ocean currents not move in the same direction as major wind surface patterns? So you would expect that ocean currents would just behave nicely, right? Wouldn't it be nice if nature just behaved nicely the way that you want it to go? But it never does. Nature doesn't care about what you want, right? Isn't that frustrating? So ocean currents don't just go in the same direction as the wind, like you would expect. They, of course, suffer from the same problem of the Coriolis effect. So wind, which is being diverted by the Coriolis effect, gets diverted. It blows the ocean currents. The ocean starts to flow, and as it flows, it gets diverted again from another dose of the Coriolis effect, and so you end up with water moving almost perpendicular to the right in the northern hemisphere, to the left in the southern hemisphere of the wind direction. So it's funny. So if the wind is blowing to the north, it's funny because your currents are going to be going directly in the northern hemisphere, directly perpendicular to the right. So that's the way everything works, right? The whole, and it's complicated too. You might remember that Ekman spiral, right? I can show you another thing here here's my business cards. Right, so if you imagine, I kind of showed pictures of this in the lecture, but you can imagine that here's a column of water, right? So here's the top of the water, the surface of the water, here's the bottom of the water. When the wind blows, all it does is moves the top of that water column, right? But so if anything, actually, you know what? I really need to do this. I really need playing cards, I guess. So here's some playing cards. It's weird I have all these cards in here inside my office. Playing cards are better. So as you move the top, you see inevitably other layers move underneath of it because the friction of the top layer is moving these bottom layers. And every single one of the subsequent layers underneath suffers from like another dose of the Coriolis force. So they keep getting diverted further and further to the right in the northern hemisphere, to the left in the southern hemisphere, from a progressive buildup of the Coriolis force. So anyway, that creates Ekman transport. Ekman transport will actually ends up moving water perpendicular to the right in the northern hemisphere, to the left in the southern hemisphere, of the wind direction. Okay, so Ekman transport is basically the water movement, that the total net water movement, current movement that results from a blowing wind, okay, a sustained wind. So it does move in different directions than the surface winds because of a buildup of Coriolis effects, okay? What are the 6 gyres of the ocean? We went over that already. North Atlantic, South Atlantic, North Pacific, South Pacific, Indian, and southern. In the Southern Ocean, you have the windward drift, a.k.a. the Antarctic circumpolar current. All right, let's go over different currents that are, made up in the gyre. So in a gyre, maybe I shouldn't draw it this way, but let's say in a gyre, you have a western boundary current, you have an eastern boundary. I did that totally opposite, didn't I? So, north, south, east. Getting myself all messed up, aren't I? West. Okay. Let me draw that better. Sorry. Give me 1 minute here. West, east. Okay. So we have a western boundary current. We have the northern boundary current. We have the eastern boundary current. We have the southern. Okay. So there's your gyre. Sorry, I drew it kind of like a square. It's not really like a square, but it's just to kind of demonstrate. So these northern and southern transverse currents, we call them, are not very important. There's not very much I can say about them, but the western and eastern ones are more characteristic in their character, I guess. Their characteristics. They're more characteristic in their characteristics. That doesn't sound good. Well, they have more characteristics that are kind of different from each other and can be contrasted with each other. I guess that's what I'm trying to say. But anyway, western boundary currents are faster, deeper, and they're also more narrow. Whereas eastern boundary currents are slower, and also, by the way, we'll just keep it at that. So they're faster, deeper, and narrow, whereas eastern boundary currents are always going to be more spread out, and they're going to be more shallow, and they're going to be more slow. Okay, so like the Gulf Stream is a really good example of a western boundary current. Okay, so a good example, like I said, of a western boundary current is the Gulf Stream. An eastern boundary current there's a lot of different eastern boundary currents. I'm trying to think of one that's maybe most important. Maybe the California current, right, is a good example, or the Humboldt current that goes along South America. Those are both pretty famous ones. Okay. So what are some of the character... Oh, no, we already did that. So be warned. I guess this is a computer test, so I'm not going to have you draw out the 6 gyres, but I could definitely test that some way and make sure in the computer you can locate. Maybe it wouldn't be so much like drawing in. I can't have you do that on a Canvas test, but I might make you, like, for example, give you a map and show you this gyre, that gyre, this gyre, that gyre, and match up the names, so you know where each of the 6 gyres are, okay? So that could be a question on the test, so be prepared for something like that. All right, transverse currents are the currents that complete the gyre. They connect on the northern and southern boundaries, the western and eastern currents, boundary currents, okay? So they're like the north-south boundary currents. They're flowing from east to west or from west to east, depending on, what the circumstances are. This is a question. What's the Sargasso Sea? Sargasso Sea is the interior of a gyre in the North Atlantic. So in the North Atlantic, the inside of the gyre doesn't have very much water flow, right? There's not much current flow there. So a lot of like floating stuff that floats in the ocean, for lack of a better word, ends up in the middle of these gyres, right? So something like sargassum. I hope you remember sargassum. It's a type of algae, seaweed, and it floats, so it's not attached to the bottom. And it floats in the open ocean. And it obviously ends up, like all floating material, a lot of it ends up in the middle of these gyres. So that's what the Sargasso Sea is. And they're really neat habitats. I didn't really show any pictures. I probably should have shown some pictures of these habitats. They're really cool habitats. Anyway, but moving on. I don't want to spend too much time on that. So where does upwelling occur? Upwelling occurs really in places where there's diverging ocean currents. So what happens is when the currents diverge, they pull apart from each other, you get fresh water pulled up from down below towards the surface. That occurs by and large at the equator. Okay, that's our main area of upwelling. All right, what's El Nino? El Nino is a seasonal fluctuation that occurs sometimes on pretty, I don't know, maybe every 7 years, 15 years, something like that. We get this, what's called the Southern Oscillation. And basically what happens is that the trade winds either shut down or reverse. And what that does is the trade winds are what is causing this divergence in ocean currents along the equator. So when the trade winds shut down, that diverging water currents cease. And when those cease, the upwelling stops. So what happens is that creates the surface water temperatures to elevate quite a bit, because you can imagine that the deeper water upwelling is cold water. So that creates hot water on top, which is much more humid. It evaporates much more. It can change all the weather patterns all over the world, okay? But especially in America, and especially in South America. I should say the Americas. What force drives deep ocean currents, thermohaline currents? It's just kind of, as the name implies, thermohaline currents. It's density differences, right, which arise from thermohaline temperature and salinity differences. So density differences, buoyancy differences, that's what drives the deep ocean currents, okay? So deep ocean currents, remember, are different than the surface currents. Surface currents are really like horizontal currents. They're, traveling horizontally, not vertically, okay? And those are powered by the wind. The deep water currents are going up and down vertically. And those are driven by buoyancy differences, okay? There are a lot of different kinds of people, oceanographers, I should say, actually split up the ocean vertically. Like they take a vertical slice of the ocean and they look at all these different layers. there are all these different names for them. I only really talk about one that's kind of interesting, and that's the AABW. That's the Antarctic bottom water. And it's kind of interesting because, like I said, at the poles, a lot of salty water, because there's no thermocline, just sinks to the bottom. And that creates the Antarctic bottom water, which is actually hypersaline. So it actually has a near saturation in salt. Okay, so much salt water builds up there. It also creates a vertical current, right? Because salt that's created during ice formation immediately sinks. Saltier water that's created during ice formation immediately sinks because, again, there's no thermocline at the poles. So that can cause downwelling in one area, which ends up causing upwelling at other areas. Okay, because whatever goes down has to come up, and whatever goes up has to come down. Okay. So anyway, be able to read a temperature salinity diagram like this. Let me just kind of explain this a little bit. So this is showing the temperature on the vertical axis, salinity on the bottom axis here, the horizontal axis. These lines that you see are contour lines showing, I can say, lines of equal density, because remember that density of seawater is affected by both temperature and salinity, right? So these are lines of equal density. So if you walk along this line, your temperature and your salinity will constantly be changing, but your density will stay the same. So one thing that I show in class is the process of caballing. So caballing is when you have two different kinds of waters with two different temperature salinity profiles, but the same density. And what I'm trying to show you with this process of caballing is that you can have two waters of the same density, but of different temperature salinity profiles. And when they mix, they actually make a denser water, which is very counterintuitive. You would expect that two waters of equal density mixing would make the same density, and they don't. So let me show you that. If, let's say we have this water A and we have this water B, they fall along the same iso bar, right? So they're falling along the same line of equal density. But when they mix, we would draw a straight line to that. We would connect them with a straight line. That would be called a mixing line. Trying to draw this line straight, it's kind of hard. So right here, a new water would be created here, C, which you notice would be denser than either A or B. Okay, so it's just something to keep in mind about how you can generate, for example, these downwelling or upwelling currents, thermohaline currents, by the mixing of two waters. Okay, that's the kind of the main point there. All right, going on to tides. So what is equilibrium theory of tides? And look, I have that written down twice, so we'll stretch that out. What's the equilibrium theory of tides? Equilibrium theory of tides is kind of the first attempt that was made to explain tides by Isaac Newton. And he tried to explain and predict tides using only astronomical variables. So, centrifugal force, the gravitational effect of the moon on the Earth, the gravitational force of the sun on the Earth, and that's it, right? Those are the only things that are going to be considered, and let's try to predict the tides from there. So that was a good kind of starting point to make a model of tides and how tides work, but it was incomplete because there's a lot of other variables that affect tides as well. Dynamic theory was suggested by Pierre Laplace a little bit later, and it takes into account many other things. So it takes into account things like the shape of the ocean basin, the Coriolis effect, geostrophic effects, things like that. So it's much more complex, and it's a better predictor of tides. Okay, so for each of the sun, moon, earth positions depicted below, please label the moon phase and then color in the moon so it properly depicts the degree of illumination. Okay, so when the moon is in this position, okay, right here, this is a new moon. Okay, so that the moon is going to appear to us to be totally dark. Okay, so I'm just going to kind of shade it in like that. When you're up here at this position, you see there's like this 90-degree angle between the sun, the earth, and the moon. You're going to have a first quarter moon. So it's going to look like it's actually going to look like this, okay? And that's how it'll look in the sky. When you're over here, you're going to have a full moon, obviously. When you're here, you're going to have a third quarter moon, okay? So that's how it's going to look when it's in the sky. But anyway, I don't know. This question's a little bit tricky because, well, I don't know. I don't even want to get into it. But just make sure you know your moon phases. But especially make sure that you know what kind of tides are associated with what moon phase. So a new moon and a full moon are going to be spring tides, which are going to be the higher tides. And that's because the gravitational force of the sun and the moon align and they work together. Whereas these, when you're at a first quarter or third quarter moon, those are going to be neap tides. And that's because the moon is working sort of perpendicularly to the sun's gravitational force. So that ends up, instead of being kind of additive, adding together and adding up and joining forces, they're kind of working opposed to each other. Okay. So why are tidal bulges on both sides of the Earth opposite of the moon? You'd maybe just expect it to be on one side, the side where that's closest to the moon, because the moon's gravitational force is pulling it up. But actually, Newton's third law, as you know, it says, third law of motion, it says for every action there's an equal opposite reaction. So on the other side of the Earth, there's also the centrifugal force that is necessary for that naturally arises from the orbit of the Earth and the Moon system. Okay, so that centrifugal force creates the other tidal bulge that happens on the other side of the planet. When you combine those two forces together, the centrifugal force plus the gravitational force of whatever, the sun and the Earth and the moon, you end up with the net attractive force. So attractive force is the net combination of all those different factors, right? The centrifugal force, the sun gravitational force, the moon gravitational force, okay? All those things add together to give you the attractive force, which is ultimately the force that creates the tidal bulge, okay? Creates the tides. All right, moving on from there. Why are tidal bulges? Oh, we just talked about it. I got so many repeats, don't I? That's why this thing's so long. And what's the attractive force? We just answered that, okay? Now, what are amphidromic points? Amphidromic points are points in the ocean, nodes in the ocean, where there's no tide. And actually, the tides sort of rotate around these amphidromic points, okay? And they actually the tides kind of rotate, almost look like they're trying to avoid them. They kind of rotate in the northern hemisphere. They tend to rotate counterclockwise around the amphidromic point, and in the southern hemisphere clockwise. And of course, some of the things that are obviously going to be, if things are going clockwise in the south or and counterclockwise in the north, one of the first things you should think of, that's probably Coriolis effect, right? So if something's happening in the north and it's happening opposite in the south, it's probably Coriolis effect. So Coriolis effect is one of the reasons we get amphidromic points. The location of the shape of the ocean basin, location of the continents and all that plays another big role in where those amphidromic points are located. Okay. All right. This one is this would maybe be like a short answer question. I talked about a lot of different animals that use tides and depend upon tides. And I'd just like to make sure that, when you come into class, taking your final, that you can think of maybe at least one example or two examples of an animal that depends upon and uses the tides. So maybe you can go back to that. I don't want to go through all the different animals again, but maybe you can go back to that part of that lecture and research that, or do a little bit. Just make sure you come into class, come into the test, you have an example of an animal that depends upon tides, okay? I gave you lots of examples in the lecture. All right, so coastlines. What would you expect to see at erosional coastline versus a depositional one? Okay, so erosional coastlines, just know some of the aspects that we see at erosional coastlines. What are some of those things? Well, erosional coastlines, you might remember, they have sea caves, they have arches, sea arches, they have stacks, they have all those structures that result from erosion, right? So you might remember that if you have this, you have some sea cliffs and a wave-cut platform. It's very common to have some like sea caves, and then you'll often have like a sea arch like this, right? And then there's a collapsed sea arch out here that's called a stack. Okay, so those are really common at erosional. You have a wave cut platform like this. It kind of creates tidal pools and things like that. Those are all really common aspects of an erosional coastline. Depositional coastlines, of course, have a lot of deposition. So when you think of a depositional coastline, you should think of a beach. Okay, beaches are really characteristic of depositional coastlines. In the diagram below, label the blanks as either bays or headlands. So remember the things that stick out. This is supposed to be the water here. Sorry, I should really paint this blue. But these points that stick out, which are made of the harder rock, are called the headlands. And these points that are made of the softer rock are called the bays. Okay? So because that rock is softer, that darker color rock is softer, it gets eroded more easily, and you end up creating these enclosed bays. Okay. Now, what are some large-scale coastal features created by sea level rise? We talked about a few of these in lecture, but fjords are one. That's when you have glacial valleys that were carved out by glacial action. Remember, glaciers flow, they carve out these deep U-shaped valleys. When those things fill up with water due to sea level rise, it creates what's called a fjord. When you have a river cut valley, you have a different situation. So let's say you have a river valley, and the river has eroded and cut this, incised this deep valley. If we have sea level rise, that will flood the valley and create a bay, just like Corpus Christi Bay. So we are a product of sea level rise. Corpus Christi Bay is, a product of sea level rise. Okay. So what were sea levels like 20,000 years ago during the last ice age? They were lower. As the world heated up, as the earth heated up, it got higher and higher as more glacial ice melted. We used to have a lot more ice sheets. Now we have two ice sheets, the Antarctic and the Greenland. And we used to have several ice sheets, right? Big ice sheets, the Laurentide ice sheet, the Siberian ice sheet, the Scandinavian ice sheet. And they're gone now, right? We only have two left. So what's the erosional coastline? What's an erosional coastline? What does a depositional coastline? What do those two terms mean? So erosional coastline is a coastline which there's been erosion. It's eating away the coastline. It's destroying the coastline, and it's slowly, the water is destroying the continent and eroding away the continent. Depositional is the opposite. Depositional is where sediment is actively being deposited, and it's actually building up the coastline, making it larger, making more land, et cetera, et cetera. So that's what those two terms mean there. There's a high correlation between an erosional coastline and the plate tectonics. So active plate tectonic margins equal erosional coastlines usually. Passive continental margins equal depositional coastlines. Okay. Now, on to marine life. You should know those 6 kingdoms of life: archaea, bacteria, those are the prokaryotes, followed by protists, animals, plants, fungus, those are the eukaryotes, right? In the ocean, what's most abundant? Probably of all those things, the protists are the king. And it's kind of a funny thing to think of, because probably you're like, I don't even know what a protist is prior to taking this class, but a protist, a lot of the plankton is protist, a lot of the seaweed is protist, right? So they're eukaryotic, often single-celled, but not always, but eukaryotic organisms, okay? So anyway, those are the most important kingdoms, I guess I can say, in the ocean. Please give an example, number 150, sorry. Please give an example of a marine animal from each of the following phyla. Porifera, you're talking about sponges, okay? Cnidaria, you're talking about corals. Cnidaria means stinging, so corals, sea anemone. You're also talking about jellyfish, right? Annelida, those are things like tube worms. They're segmented worms. Basically, Annelida's segmented worms. Tube worms, the feather duster worms. Okay. Arthropoda, any crustacean, crabs, shrimp, so many other things I could mention here. Mollusca, those are things like clams, sea snails of any kind. But also octopus and squid as well. Echinodermata, those are things like sea cucumbers. sea lilies, sea stars, and finally chordata, chordates. Those are things like fish, so many things, sea turtle, all the nice, fluffy, cute things that live in the ocean. Probably everything that you like that lives in the ocean is probably chordata, right? Like fluffy seals and cute little sea turtles and things like that. So, but anyway, that's chordata. So it has a notochord. What are the differences between planktonic, benthic, and nectonic fauna? So planktonic, benthic, nectonic. Planktonic means that you are carried by the currents. Okay, you're carried by, you have basically no control over where you go. Okay, you're carried along by currents, carried along by tides or whatever. Benthic means that you live on the bottom of the ocean, and you don't live in the water column, but you actually live on the seafloor. Nectonic means that you are a swimmer. So you live in the water column, but unlike plankton, you can swim and you have some control over your own destiny. You have control over where you go. All right, what's the difference between autotrophic and heterotrophic organisms? Autotrophic means self-feeding. Heterotrophic means other feeding, so feeding on other things. So heterotrophic organisms eat other things. Autotrophic organisms feed themselves. So basically they're either photosynthetic or they do chemiosynthesis, which you recall is a common mode of life for creatures that live at mid-ocean ridges, right? So it's basically the autotrophic organisms form the base of the food chain, and then heterotrophic are consumers of various kinds. Number 53, last one. What's the difference between phytoplankton and zooplankton? Phytoplankton is plankton that is plant-like and autotrophic. Zooplankton is heterotrophic plankton that eats other small organisms. Okay, there we go. We're all done. It was just about 1 hour and 1 minute. Okay, so just what I was hoping for. So anyway, study hard for your final, and I will see you on that final day. And good luck.